right, so we're going to be talking about exponential growth and decay. So we've already talked about exponential functions. So a growth occurs when our quantity increases by the same factor over equal intervals of time. Okay? So when you look at an equation for exponential growth, you've got y equals a, so there'll be some number right there, and then 1 plus, all right? It's like taking 100% and adding a rate to it, all right? Raised to the t power, where a is bigger than 0 and r is also bigger than 0. That is an exponential growth. So this r represents your rate of growth in decimal form. So if I said 8%, you would take that and move your decimal point 2 places here. That would be 0.08 as a decimal. So always plug in the decimal form when you plug in for your rate. T represents the time, maybe 1 year, 2 years, 3 years, whatever. The initial amount, that's the amount you start with, and then your final amount. So exponential growth might be if I invested some money and it was growing over time, right? So however much I invested would go right here. The rate or my percentage that they give me, how many years, and then y represents the final amount, okay? And then this part right here in the parentheses represents my growth factor. So a decay is the same thing, only instead of increasing, we are decreasing. And the only thing different in our equation is that there is a minus sign instead of a plus sign, okay? So on number 1, the inaugural attendance of an annual music festival is 150,000. So annual means every year, right? So let's just get a few words out of the way. If I say annual, that means I'm talking about something that happens every year. If I say semi-annual, that means that's going to happen twice a year, right? Think about like a semicircle is half of a circle, so semi-annual is like half of a year. So 2 times a year. If I say quarterly, that means I'm taking my whole year and I'm cutting it into quarters. That would be 4 times a year, okay? So you got to think about how many times this is happening. The attendance Y increases. So since we're increasing, we have a growth by 8% each year. Now, when we plug into a formula, are we going to put in 8%? No, we're going to put in 0.08. Move that decimal 2 places to the left. So this represents my rate, right? I like to put this on there, growth. I know I have a growth. And it says that the inaugural attendance of the annual music festival is 150,000. So that would be my initial amount, which is represented by the letter A. So it says write an exponential growth. It even tells you have a growth, even though we already decided that. Growth function that represents the attendance after T years. So it didn't ask us how many years, right? It just said write a general equation. So for part A, we have y equals. And since this is a growth, I'm literally just plugging in right here. So my initial amount, that's my A. I'm going to put the 150,000 in right there. And then I have a parenthesis, and then a 1, and it's a growth, so a plus sign. And then you're going to insert your rate. Your rate is 8%, so 0.08. And then it says to the T years, so we're just going to put a T up there. And there's the equation. So we can figure out how much the attendance would be any year that we want, right? So part B is where that's going to ask us that. How many people will attend the festival in the 5th year? Your years is represented by the T. So we're going to plug a 5 in for T. So we have y equals 150,000 times 1. Now, I could actually put this together as 1.08 instead of putting the 1 plus 0.08. And then I'm plugging in the 5. And then all I have to do is plug that in, and that's going to tell me how many people they expect to have in the 5th year. So I just plug it all in just like that. All right, so we are estimating, right? Now you can't have, 20% of a person. So we will just round down to the closest whole number. So they're expecting to have 220,399 people. So 220,399. And this is people, right? And it did say round your answer to the nearest 1,000. Oh, to the nearest 1,000. So this would be rounded to the nearest whole, right? So we're rounding to the nearest 1,000. So we have 220,399. So this would be the 1,000 right here, right? 220,000. And since that's less than 5 after that, this would be 220,000 people. Make sure you read the directions, unlike me. All right, number 2. A website has 500,000 members in 2016. So that 500,000 is going to represent the A because that's our initial amount of members. The number Y of members increases. Okay, increases. That means that we have a growth by 15% each year. Okay, 15%, that's going to be our R. But instead of 15%, we're not going to plug in 15. We're going to plug in 0.15 because we're going to move that decimal 2 places to the left. Okay, part A. Write an exponential growth function that represents the website's membership T years after 2016. So just a general equation, we're going to keep the T. So we have Y equals our initial amount, 500,000, times, and then we have 1, it's a growth, so plus, and then you put in your rate as a decimal, 0.15 to the T power. So we have our equation. Part B says, how many members will there be in 2022? Round your answer to the nearest 10,000. All right? So let's look at this. We have Y is equal to, and then all we're going to be plugging into is this T right here, so we need to decide what number to plug in there. And I'm going to go ahead and say 1 plus 0.15 is 1.15. And then it says 2022. Now, T represents the years after 2016. So how many years would 2022 be after 2016? 6 years. So I'm going to plug in a 6. And then I'm going to go plug this into my calculator. So I plug that in. And I get 1,156,530. So it said to round to the nearest 10,000. So this is the ones, the tens, hundreds, thousands, and then 10,000. Yes? So I'm rounding to this place. So I look back here, and I have a 6, which means this is going to round up to a 6. So 1,160,530. So we have 1,160,000 members. Always put whatever your unit of measure is. Members, people, dogs, cats. All right, so number 3. We're going to determine whether each table represents exponential growth, exponential decay, or neither. So to do that, first you always want to make sure that your x values are increasing at the same rate. So I'm just adding 1 every time, correct? All right, so I'm good there. So now I'm going to look at the y's. So as my x increases, my y's are getting smaller, correct? And so I want to make sure that it's the same amount every single time. So what I can do is I can take and I can decide what's happening every time. So I'm cutting down, and sometimes it's easier to look at the smaller numbers, all right? And I like to put little things out here to show what's happening. So to get from 270 to 90, what would be happening? I'll tell you an easy way to do this. You're going to take this one and divide it by the one above it. So if I take 90 and divide by 270, that gives me a third. And if I take 30 and divide that by 90, that gives me a third. And if I take 10 and divide that by 30, that gives me 1/3, right? So the bottom divided by this, that tells you what you're doing, right? So I'm cutting these by 1/3 every single time. And if you think about it, 270 divided by 3 is 90, right? Divided by 3 is 30. Divided by 3 is 10. Or 270 times 1/3. That's the same thing as dividing by 3, right? So I am multiplying by 1/3 every single time. And I know I'm getting smaller, so that makes this an exponential decay. So if we take a look at part B, x's are going up by 1 every time, so I'm good there. So to decide what's happening, these are a little easier. Obviously, my numbers are going up, right? But I need to make sure that I'm multiplying by the same thing every time. So looks like to get from 5 to 10, I would be multiplying by 2. And to get from 10 to 20, I would multiply by 2. And to get from 20 to 40, I would multiply by 2. So since I'm increasing, this will be an exponential growth. Now, if you were to choose neither, that would mean that I wasn't multiplying by something every time that was the same. Maybe it was, a third, and a half, or something. Or I might be adding the same thing every time. That's not exponential. So if I was adding to, adding to, adding to, that would not be an exponential thing. That would be a linear thing, all right? So you have to make sure you're multiplying by the same thing every single time. All right, so on number 4, we're going to determine whether each function represents exponential growth or exponential decay, and then we will identify the percent rate of change. So remember, inside this parenthesis, that represents either 1 plus something or that represents 1 minus something. So if the number is above 1, then that means that that's going to be a growth. If that number, for instance, like on part B, is less than 1, then that's going to make a decay. So if you look at this, that would be a growth. So exponential, I'm going to abbreviate growth. And then you have to tell me how far above 1 that is. It's 0.07, right? Well, 0.07, I'm going to put my R here as 0.07. I want to change that to a percentage. So I'm going to move my decimal 2 places this way. So that would be a rate of change of 7%. All right, so I feel like the growth ones are a little bit easier to identify the percentage in which you are going up. All right, but if you look at this one, that one's going down, right? This is a decay because it's smaller in the parentheses, is smaller than 1. So I have an exponential decay. And then you have to tell me how far below 1 that is. So I know that my rate is 0.98, right? How far below 1 is that? Actually, I don't want to write the r as that. That might be confusing. To find r, you have to take 1 minus the 0.98. Think about it like money. What's a dollar minus 98 cents? That's 2 cents, yes? So my rate is 0.02. Move that decimal 2 places to the right. So I have a decay of 2%. All right, so we're going to do the same thing on number 5. So I'm going to look at in the parentheses, right? That's smaller than 1, so this will be an exponential decay. And then we need to decide how far below 1 that is. So I'm going to take 1 and I'm going to subtract the 0.96. So when I do that, that's going to give me 0.04, right? Take 96 cents off of your dollar. So my rate is 0.04. So as a percentage, that would be 4%. So I have an exponential decay that's going at a rate of 4%. Part B, look inside the parentheses here. Oh, y'all, I am not paying attention in this whole video. All right, we got to stop for just 1 second. We're going to have to redo this one. Because, do you guys see this right here? Way up here, it's really small. Let me zoom in. Oops. Struggling today. Where's the zoom in button? Right there. That's not a t, is it? It's a t over 4. Well, that means that this equation needs a little bit of work done to it. So we're going to have to do a couple of things so that we have just a t up here. So I want you to think about this. I have t over 4. That is the same thing as 1/4 times t, right? And then I need just the t to be out here. Well, if you think about your properties of exponents, if you're multiplying these, then that means that this 1/4 was the exponent of whatever was in here. So this is like 0.96 to the 1/4 power raised to the t. Because remember, when you have a power to a power, you multiply those, right? So you're kind of working backwards. So you need to figure out what this number is inside the parentheses. So in my calculator, I'm just going to plug in the 0.96 to the 1/4. And that gives me, we'll just round 2 over, so 0.99 to the t. So now we just have the t out there, correct? Still a decay, right? Because this number is smaller than 1. So I still have my exponential decay. But my rate's going to be a little bit different, right? Instead of 0.04, it's really just 0.01, which would be 1%. So I will apologize for that. Also, if you guys notice on this one, in the directions, it just says determine whether it's exponential growth or decay. Did it ask for the rate of change? No. So we really didn't even need that part. We did extra work. Don't follow my lead. You guys should always read the directions. All right. So let's take a look at part B. If you notice, part B has the -3 up there with the t. So we have to get this to where there's just a t up here. So let's think about this. What causes us to subtract in the exponent? Well, that would be when I have the same base and I take the top exponent and I subtract the bottom exponent. So when I have two things that I'm dividing where I have the same base, I subtract the exponents, right? Well, this represents my top part, so I want you to think about this. This would be like me saying 1 over 1.1 to the third power times 1.1 to the t. Because if I put them back together, this is over 1, right? And I can just multiply tops and bottoms. So if I have something on the bottom, I can move it out to the side, and then I want to decide what this is. So 1 over 1.1 to the 3 gives me 0.75. So this is 0.75 times 1.1 to the t power. All right, so now I can look at that and say I definitely know that that is a growth. So exponential growth. And if I was deciding this will be a 10% growth, right? Because I'm 0.1 above, I would move 2 to the right, that would be a 10%. So we're going to do the same thing on number 6. Notice that I am adding this time. So what causes me to add exponents? Well, that would be if I had my 0.95 to the t times a 0.95 to the second. Then I would be adding those exponents, right? So I'm kind of working backwards. So I'm going to go ahead and decide what 0.95 to the second power is. That gives me 0.902, so 0.9. Now, normally, that would be in the front, right? So 0.9 times 0.95 to the t. And I'm going to look in that parenthesis there now that I have my power of t by itself. And I notice that that's less than 1. So I'm going to go ahead and state that that would be an exponential decay. Take a look at part B. Again, notice t is not by itself up here, so we're going to have to take care of that. So what causes me to multiply two numbers in the exponent? That would be if I had this 10 inside and the t on the outside. Then I would do 10 times t, which gives me the 10t. So I need to decide what 1.02 to the 10th is. Which is 1.22 raised to the t. And then once you get that t by itself, you look in the parentheses. That's bigger than 1, so this would be an exponential growth. All right, compound interest, that has a different formula. When you compound interest, is the interest you earned on a principal and on previously earned interest. So in other words, if I've invested something and I've earned some interest and that's added to everything I put in, and then I start earning interest on that part as well. So that's what we call compound interest. So the balance of an account is equal to this equation, right? P is your principal. Principal means the amount that you put in, your initial amount. Your rate, that's still your interest rate in decimal form. And then you have n located in two spots. One is underneath the r, and one is up here in the exponent. All right, that represents the number of times you compound in a year. So remember, if I say yearly, that's 1 time a year. If I say quarterly, that's 4 times a year. If I say semi-annually, that's 2 times a year. If I say monthly, that's 12 times a year. Okay? And then how many years I end up doing that is the T. So you deposit $100. That's my initial amount, so that's the P, right? I'm just going to make a list down here. So P is 100. I deposit that in a savings account that earns 6% annual interest. By the way, you're not going to be getting 6%. Okay? That's like way high. It earns 6% annual interest. Okay? So I know that my rate is 6%, so that would be 0.06. Annual interest compounded monthly. So n represents how many times I'm compounding, and monthly, there are 12 months in a year, so that's 12 times. Write a function that represents the balance after t years. So t should be left in our equation for the years. Everything else gets plugged into. So I have y equals p, that's my initial amount, times 1 plus my rate, 0.06, over how many times I compound, that's my n, so 12, raised to the n times t, so 12 times t. Now, I don't really like for you to leave this middle part in the parentheses like that. I'd rather have one number in there. So we are going to figure out what that is. 1 plus 0.06 over 12. 1.005 to the 12t. And there's my equation. So if I wanted to know how much money I'd have in my savings account after, 6 years, then I could plug in, 6, 7, 8, 9, 10, any into this equation. So I have an equation that would tell me what I'd be earning. All right? Okay. You deposit $500 in a savings account, so your principal is $500. That earns 9% annual interest. Okay, so my rate is 9%. That would be 0.09. Compounded monthly. So every single month. That's 12 months in a year. And we're going to write, it says and graph. We're not going to graph that. A function that represents the balance after t years. So I've got y equals my initial amount. That's 500 times 1 plus, and then I'm going to put in my rate, 0.09 over 12, and then raise that to 12 times t. All right, and now all you have to do is figure out what the 1 plus 0.09 over 12 is. $1.0075 to the 12